Welcome back, Generals, to another Let's Fix Generals 0 Hour to make the best game ever. Good, so we probably want to do some reviewing. First, same. Follow up and applies additional spelling, grammar, and consistency fixes to comments across all any files. Let's take a look. 2000. Okay. Oh boy. The scrolling is strong on this one. Yeah, very strong. So a lot of milliseconds. Yeah. MSEC. Take no damage if there's no one to pass this to. Fantastic. Milliseconds. Okay. Follow through. Okay. Particles can't do damage. So this is a fast shooting low. What? Particles can't do damage, so this is a fast shooting low damage. Better pull low damage to a single line. Bigger number. Okay. Great. About the weight of a grain of salt. Great. It's a lot of the same stuff. No. Great. Takes no end here. Just keeps on going. There we go. Good. Proof. Good. Then next code. Yeah. So. Let's see what is approved. Okay. Nothing to merge here. Better change the default to then the codes can be simplified. Okay. Okay, what else can we comment about this? Let's take a look at the actual implementation. Average FPS, low 1. Mm-hmm. 1%, okay. Mm-hmm. 5 seconds. What? That's kind of massive, isn't it? um. What? This compiles with VC6. Ends elements. It does. Okay, interesting. Didn't know that. Okay, so my first hunch here, without digging deep into the implementations, is that this looks very overcomplicated here. Like, why do we have 5,000 samples? And this 3 times. What is this? Let me get a calculator here. So 4 times 3 times 5,000. 60,000 bytes. So divided by 1,000, 24. That's 58 kilobytes. That's 58 kilobytes here. That's outrageous. This is absolutely outrageous here. Because it also takes a lot of time to iterate this shit. So history count, I guess this one reaches. I'm baffled. Like, why is this so large? How large is it currently? Get average FPS. Let's take a look at the current implementation here. Average FPS, how's this calculated? Sum, accumulate, FPS history size, 30. 30. Yeah. Yeah. So $30. This one is 3 times 5,000 elements. So, why 5,000? Covers 5 seconds at 10,000 FPS. At 1,000 FPS. History size. History count. So I wonder how large does this get now? This history count. I'm shaking my head here. This looks outrageous here. So, history offset. So, as long as this is smaller than history count, it will keep rising. So, once it reaches 5,000, then it stops. Yeah. Until then, it keeps on increasing. No? Okay, fair enough. Mm-hmm. 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 Yeah. Max. Bottom sample. Max. Mm-hmm. It's also three. It's also three buffers, not just one. So this is one sort buffer. Hmm. Hmm. But what also looks strange to me is that even if our even if we just have 30 frames per second, it will still go through these 5,000 samples, right? Or will it drop off older ones? Where do we add and remove samples? Here. Mm. 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 Mm-hmm. I think I need to see the debugger. Mm. Let's do a stash. 1% low. What's his name? 1% low. This one. Mm. Mm. So mm. How is this possible? Okay, I would say if this function is called with 11 seconds or 0, there must be something wrong. If this is called with 0 time, 0 seconds, then it indicates error. So history offset. Yeah. History offset -1. Yeah, it always starts at I. History count. To me, this looks weird. To me, this looks very weird. I expect that this is wrong for slow frame rates. That it's just the FPS will be way too smooth now. But I'm not sure. I need to check in debugger. History count is 0. Current FPS count. Can we get rid of this check? G by starting history counts with 1. Sample count. Well, it's redundant anyway, because sample count will be 0. So it will also, this test is redundant. It will already exit here. So let's take a look at everything is slow. Boah, it's extremely slow. Boah. So, by the way, let's get the latest code. Fetch and prune. So, so let me take a look at this here. So, history count is 163 right now. So it will loop from. But there is a break here. Let me compile it with debug. There's a breakdown here times sum. But shouldn't this be starting at offset? History offset index. It does here. So history count is 611. History offset is also 611. What? Okay, so it will only visit a subset of this buffer. Windows seconds. What is that? 0.5. Wasn't that 1 second before? Windows seconds. Windows seconds. We go to in-game UI. Render refresh MS. So what is this set to? 1000. Okay, then we can say here, is it? Can't find it. 0.5F. There we go. This is half of the update rates. This is just half of the in-game UI update rates of 1 second. Why is this here? Time get time. because he doesn't want to update it so often, I suspect. Okay, I suspect the goal here is that it's not updated every frame, but only once in a while. This interval is a bit unfortunate here. This is for performance reasons. Can we make this cheaper instead? Yeah, I'm not a fan of this here. Also, the system core is expensive. Can we get rid of this condition? Looks like it will almost never be true. Never be true. So So I wonder if there's a way we can reduce this sample count. Yeah. Um. Can we get rid of this condition? Looks like it will almost never be true. Perhaps init history counts with 1. Okay, so how can we simplify the samples? Now I need to do the thinking here, even though it's not my change. But to me, it looks like that there's a better solution to this. It can't be that we need to have 3 times 5,000 samples, 4 bytes floats. I guess 60 kilobytes for this. It's outrageous. The size requirement is just outrageous. And it needs to read this every frame, and especially if you have high frame rate, it needs to go through all these buffers every frame through these 60 kilobytes just to get these counter values. That's insane. It's insane. So it seems like not much, but just for this one counter, this many bytes is just insane. So this really needs to be second guessed. I wonder if there's a simpler solution where we can. We have. Well, it's tricky. Yeah. It is tricky. Yeah, he noticed the same thing. 60 kilobytes just for the FPS checkers. The question should be given 3 seconds time frame, 1% lower. What 3 seconds average FPS? Is a low FPS no longer relevant? Say you average 300 FPS. What is the chances that 1% is so low that it's still relevant as a performance metric? 300 FPS is the upper bound, only 900 samples need to be stored. It's only 80% of the memory. Average FPS, 30 FPS lows. Yes, the size requirements for the FPS counters are outrageous. Okay, but how do we optimize this? Covers 5 seconds. Okay, let's say I have an idea. You can significantly reduce the size and computation requirements by organizing intermediate results in buckets. So for example, say how do these look like? Here, so FPS history, and then so this, let's say this is 30, and then you have so 30 is let's say FPS bucket, so 30 samples. say average FPS buckets, and then I don't know. Could also have like 30 maybe, yeah. And then low FPS buckets, also 30. For example, have that. So this one lasts 30 frames. Average FPS over lasts 30. Average FPS over lasts 30. Last 30 times 30 frames. Min FPS over last 30 times 30 frames. Basically create checkpoints for chunks. This dramatically decreases. Well, but these buckets, so these are frames, so yeah, so the disadvantage is that you can't really say, you can't do this precise timing where you say, hey, well, you have an average. The average is, I think it's okay. It's okay. Reasonable chunks. This decreases accuracy. Let's say time decreases time. Well, if you have the average FPS, with the average FPS buckets, you can still calculate reasonably accurate time regions. No. Well, the problem is, so for average this would work, but for low it's a bit more tricky. Yeah. Well, yeah, for the lows it's a bit tricky. Maybe. Yeah, I'm not sure. So for average, I think this approach is fine. Yeah, because it's pretty stable. Like, doesn't matter if we average, like, you know, if we average 500 samples or several times 30 samples. In the end, like if you add them all together, if you average those averages, you get like a final average. Like, so if you average this one, you get like a representative average. But with the low buckets, so we're looking at 1% lows, yeah? Then maybe the bucket should be 100. Well, let's say, so this one is 100. Yeah, this 100 and this 30. So from this year, from this here, you can take a 1% low, which is one sample, the lowest sample you take from this. But it's also, yeah, but it means that, let's say you have, okay, so the problem with this is, if you have several big stalls in here, then it might be underrepresented in these low FPS buckets, because you can have like 29 that are, you know, relatively fast, but then you have this one bucket that had a lot of low samples, but you only take like one of them, right? So how would we mitigate this problem? Well, for average, we probably only need 1 second, so we can do 10 here. So this is 3000 frames, this is 1000 frames, which is enough. Yeah, so average FPS buckets is fine. Yeah, that's fine. Yeah, so the buckets. Yeah, so for average FPS it's relatively okay, but for low FPS bucket, it's a bit of a problem. Can we maybe? Let's say. Yeah. Yeah. So basically, the lows could be too optimistic. Yeah. Hmm. Yeah, it's not very accurate for the mins. For the lows. Is that acceptable? Probably not. Yeah. Yes. I mean, the data size this way would be much better. No, much better. Okay. Maybe there's another way where we can have like running counters. Let me ask ChatGPT. Um, mm, can you propose a implementation proposal? Well, can you propose a implementation to calculate average to sample and calculate average and min and 1% low FPS value over the duration of 3 seconds with minimal data size and computation requirements. I wonder if there's like implementation where we can have like a value accumulators. So we accumulate values and then we divide by counts. So for average this would work, right? You count you count the time length and you just add them and you divide by the number of samples, right? So you just need two values for average. But for min, for lows, can you propose implementation to sample and calculate average and 1% low FPS values over the duration of 3 seconds with minimal data size and computation requirements? Yeah, so for average, we only need one counter to accumulate the to accumulate the times and divide it by the number of samples. Yeah, that's the simplest implementation. 2 values, no buckets, nothing. For lower FPS, I don't know. Maybe there's a way. Let's see what it says here. Let's see. Rolling 3 seconds. Very little memory. Store recent frame times, milliseconds per frame for the last 3 seconds. Why frame times? Because FPS is non-linear, yeah. So sample frame ms. Maximum samples needed 1000 FPS, worst case. 3 seconds window, 3000 samples max. So he's also suggesting 3000 samples. Ring buffer with timestamp accumulation. Average FPS, total frame ms divided by frame counts. Yeah. So this one is like the cheapest. Yeah, that's what we got already. Efficient 1% low computation. Since the window is small, a few hundred samples normally, the cheapest implementation is copy frame times into a temp array. Use partial sort, nth element, average worst 1%ers, convert to FPS. Okay, so the first comment we can already add here. This implementation is very inefficient for average FPS. The simplest average FPS can be 0.1 by doing frame time sum divided by sample count. Average frame time sum divided by sample counts. So all of this here can already be simplified to very efficient accumulator. Yeah. Well, the only problem is then. Yeah, but the problem is, how do you? So there's a problem though, because how do you know what to kick out? Like, so once you reach your favorite length, sample length, do you still need buckets then? Yeah, we can't do this because this would only work if we just keep sampling forever, right? Like, we would need a checkpoint where we can throw out older ones. So we would need the buckets. Yeah. However, that is not. That is not. That will not work here because I need to throw away old samples. Maybe we can let me continue here first. So let's try to understand. So this one is also suggesting nth element. Yeah. Tiny, 12 kilobytes. CPU very low. 0.1 per frame. N only when refreshing stats. Important detail. Quantize frame times into buckets. Okay, that's what we were thinking. Yeah. Maintain rolling histogram. Average FPS from running sums. Yeah. Into these buckets. From histogram traversal. What is that? 1% low from histogram traversal. Okay, I don't know what that means. More implementation complexity, quantization error. Yeah. Usually unnecessary unless profiling on consoles embedded systems. Let's refresh. Okay, can you elaborate on 1% low from histogram traversal? Very efficient approximation technique for rolling frame time statistics. You want strictly bounded CPU cost. You avoid temporary array sorting. You run on constrained hardware. You want deterministic performance. Yes. Slowest 1% of frames. Slowest frames, largest frame times. A histogram already tells you how many frames fell into each frame time range. Okay. So you make histogram buckets. I see. I see. So, yeah. But the problem here is also you don't know which ones to throw out now from these counts. Like you add counts, but when do you know when to remove these counts? So I don't think that this approach works. Well, you would need buckets of these ranges. Ugh. Well, that's not much simpler. Yeah, you would need a bucket with ranges, but then these ranges, they're kind of limited, right? Frame time buckets, not FPS buckets. Hmm. 800 bytes. Remove all samples. Yeah. It's not great either with these histogram buckets. Can improve precisioning, hybrid buckets. Yeah, I'm not sure about this. Yeah, it also looks very complicated and you lose this precision. Yeah, maybe. Maybe we can have. I would still go back to this here. So, what if we say, let's say we do FPS history 10, it's 10 frames. Then we do 100 here and 300 here. average FPS buckets. 100. So basically, so this would now contain 100 times 10 and this 300 times 10. Last 10 frames that go into a new bucket when complete. But then this won't work because here you can't get a 1% low out of. Well, I can. Well, you need to. I'm not sure about this. You may ask ChatGPT. So do float here. Could we perhaps well, for average FPS, could we perhaps organize the organize the values like so to reduce the data size requirements. What are the implications? Hierarchical downsampling design is much closer to how real telemetry systems work, blah. So frames aggregate small buckets, aggregate long-term statistics. This drastically reduces storage requirements and can still produce good-looking metrics. The main question becomes, what statistical information gets destroyed? Yes. What determines how accurate your 1% low remains? Yes. Frame micro windows feeding 1000 frame macro history. This works well for average FPS, compresses extremely well, yes. With almost no meaningful information loss. Yeah, because averages are associative, yes. Problem 1% load does not compress well, yes. 1% low, terrible. Average 50 FPS. Minnow B, average also 50. 1% low is completely different. You destroy spike distribution information. Yeah. %1 low of pre-aggregated lows, which is not equivalent to true 1% low. Introduce bias. Artificially optimistic. Yes, because spikes are diluted. Yes, it's very right. Very true. I'm impressed by how smart this AI is. Example of failure case. Bucket 1, bucket low. Yeah, bucket 2, 60, bucket low, 60. Later aggregation averages these lows. But true worst 1% frame was 5 FPS. The stutter severity got washed out. Worst frame time observed in each bucket instead of low FPS averages. Because maxima preserves spikes much better. True. Recommended compressed design. Instead of FPS values, store frame times. Frame buckets. Average. Max. True. Max. Then each bucket summarizes. Where not max. Max, the highest. The highest. The highest is the lowest FPS. 10 frames. 1% low approximation. The slowest frames dominate. Computing approximate 1% low from 300 buckets. Collect all max frame MS. Sort, select worst fear. Average, convert to FPS. Worst spikes over long duration. Very effectively. Storage costs. Thread floats. Already tiny. Store microseconds instead. Microseconds. Time-based buckets. 50 ms buckets, 100 ms buckets. Why? Frame count buckets distort under FPS swings. True. Time-based buckets. Okay. I think that's a good direction. Without having seen implementation and how it actually looks, but I think it's important that I would say the performance of this is more important than the accuracy. It's fine if it's a bit less accurate, but it just needs to be fast. The speed is more important than the accuracy. Yeah, like if a player looks at these values, he doesn't care if it's 1-2% off. Yeah, it doesn't matter. The accuracy, it doesn't need to be scientifically accurate, but it needs to be fast. That's the most important. So let me check again this suggestion here with the microseconds. Why store microseconds? So that means microseconds, right? So that goes up to 65 milliseconds then. 65 milliseconds frame. Okay, but 65 milliseconds, that's not enough. Like a frame could spike longer than that. Yeah. Yeah, I don't like that. It would be great though if we could store average and max. Well, we could round this as well. Mm-hmm. Mm-hmm. Let me draft it in a notepad. So let's say FPS bucket. I mean, if we need for FPS, we need at least 100 milliseconds. 100 milliseconds, that's 10 FPS, right? Let's go, I mean, 1 FPS. So 1000 microseconds, but that won't compress in there. Let me see. So 1 million divided by, let me go to programmer. 1 million divided by 116. 15. 15. So if we divide the accuracy by 15, maybe we can do yeah, so, for buckets, whoops, for buckets, for struct buckets, we probably want to be able to store up to 1000 milliseconds. Can you add set and git methods that lower the resolution of the microseconds to accommodate accommodate such a large range. So we should see some division multiplication by 15 roundabout. Let's see. Yes. So 1000 milliseconds is 1 million microseconds. You must quantize, compress the value. So times 16, he says. Okay. Simple and effective design. Use 16 microseconds resolution, which covers that much milliseconds perfectly. So 0. But that's 0.016 milliseconds. Error. This is extremely accurate for FPS telemetry. Frame time 1 ms, smaller than 1%, quantization error. Yeah, I think that's good enough. I mean, frame time of 1 millisecond is just outrageous. If we get it, it's 1000 FPS. So that would be pretty good. Yeah, I think that's a good idea. Recommended struct. Quantum. Encode US. So average 16 US. Oops. Quantum US. Float decode US. Is that correct? Encode, float, get decode, get average MS. Yeah. Clamp. Okay, so this looks very promising. Yeah, so basically have so these are 4-byte buckets. Yeah, 4 bytes. The data is compressed into these quantized 2-byte values. So ranges from 0 to 65,000 something. And then with the scaling, it ranges beyond effectively 1000 milliseconds. Yeah, once you encode decode it. So this is pretty accurate. Yeah, encode, decode. So get average US, decode, just a multiplication. Yeah, so that's extremely fast. 4 bytes per buckets. It's 1200 bytes total. Yeah. 16 resolution is much finer than monitor refresh. Even at 360 hertz, 2.78 milliseconds per frame. So 8 milliseconds per frame. Coding decoding is multiplied, divided by constant, very cache friendly. No floating point complexity needed. Integer only variant. You can make it fully integer based. No, I think it's fine. Advantages, no FP conversion. What does that mean? No FP, no floating point conversion. Okay. Precision is better. 8 microseconds. Yeah, no, we don't need that. That's fine. 60 microseconds is the sweet spot. Yeah, I also I think this one is good. 1000 milliseconds. If you care more about low frame times, no, it's also about average. Use nonlinear encoding, example, logarithmic quantization, float 16 like encoding, high precision, lower precision. Okay, complexity rises. Yeah, no, it's fine. Yeah, I think this the first suggestion is already fine. I do find this one interesting though. Make it fully integer based. Um, mm-hmm. Yeah, I think that's better. Quantum shift 4. Hmm. Yes, please use the integer based encoding and add a comment, add a explanation to the struct. Mm-hmm. A bit less, please. Not so much. Okay. Static cast. Average US. Yeah, I think that's better. Mm-hmm. Quantum US, quantum shifts. Mm-hmm. Okay, I think that's a great suggestion. I inquired a bit with Chat GP, and we can reduce size requirements by quantizing samples and moving intermediate samples into timed buckets. So this one is the here's a sample. Here's a sample. It's a sample frame bucket with average and min frame time stored in 2 bytes each with a resolution of, what was it? Resolution of 16 microseconds. And then Then we need to move these frame buckets into a time-based array. Can you also make a sample? Can you also generate a sample implementation using the frame buckets in an array to generate sample implementation using the frame buckets in an array for 3 seconds. For 3 seconds. How much buckets do we want to have? I think we talked about this before. 300 buckets. Yeah, so basically 10 every 10 milliseconds, one bucket. Oh, hold on. So 3 seconds. So it's 3000 milliseconds. Yeah, so divided by 300 is 10. So every 10 milliseconds, we sample the lows. Yeah, sample implementation using the frame bucket, an array of 10 seconds every 10 milliseconds. Yeah. I copies all this shit, okay. FPS history, add frame. Simulate 60 FPS. Yeah. So bucket interval microseconds. So that's 10,000 history seconds, 3. So bucket count, history seconds multiplied by 1 million. 1 million, yeah, divided by 10,000. Okay, yeah. So that should give 300, right? So that would be then 300 times 4, so 1200 bytes. Find worst bucket maximum frame time. Yeah, there's still things missing in here, but I think I just want to demonstrate the approach. Yeah. Then we move these from into a time-based array. Sample implementation. Well, actually, let me ask. So where does he have add frame? While bucket elapsed as emit bucket accumulate stats for current buckets. Emit one or more buckets if enough time elapsed. I see. Emit bucket. Okay. Yeah, it looks about right. Yeah. Good. Let me copy this here. The thinking this effectively uses 1200 bytes. This uses just 1200 bytes for just 1200 bytes at most. Because the implementation this data organization approach uses just 1200 bytes at most. It loses some accuracy. But this should be practically inconsequential. Sequential. We optimize for speed over accuracy. Yeah, so that's my 2 cents on this. Yeah, so we have 300 frame buckets these are the max number. Yeah. So so it's the with 300. Well, means so the only downside of this now, so it will be cheaper for high FPS, but it will be a bit slower. Maybe for low FPS. So if we had 30 FPS, then we only need 30 samples. We have 1000 FPS, we need 1000 samples. No, that's not. So, yeah. So for average FPS, so if we have 1000 FPS, it would need 1000 samples. For 30 FPS, just 30. But with our buckets, we always go through these 300 now. Yeah. So at 30 FPS, the cost actually will be a bit higher, right? Yeah, so that's not so great. The cost is higher. Yeah, so there are still downsides here. Maybe we can do with less buckets. Let me ask. How many 10 milliseconds. Yeah, so the problem is that, well, array for 3 seconds. What if we make it larger? 50 milliseconds. 50 milliseconds. Let me say with the bucket size, with a bucket time length of 100 milliseconds still be acceptable? What is your recommendation? 100 ms buckets are still acceptable for a lightweight telemetry overlay system, but there are important trade-offs. 10 milliseconds, excellent. CPU higher, memory higher, spike, excellent. 50 milliseconds, very good, low, low. 100 milliseconds, acceptable. How much temporal detail survives compression? Small buckets preserve short stutters, frame pacing, irregularities, micro hitches. Large buckets smooth them away. Yeah. Hmm. Five smooth frames, one hitch. Mm-hmm.  Different systems use surprisingly coarse windows. Medium per frame, 50 to 250 milliseconds. 50 milliseconds. Mm-hmm. 3 frames per pocket. Good spike preservation. Mm-hmm. But if you have a no. Mm-hmm. 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 Bucket intervals could also be longer. Could also be longer for even. However, your current implementation would perhaps be more efficient at low frame rates because less values are stored. I suggest to look into this, how to find a good balance between speed and accuracy, between size and speed, size, speed and accuracy. Mm-hmm. For even less size. This waves need reading at small frame counts. The current implementation. Yeah, so there are advantages and disadvantages. So basically, the proposed implementation here is very inefficient at high frame rates. It always consumes this much memory. At lower frame rates, there's less work here because it will have less sample points to look into. Yeah. But when you have like 1000 FPS, it hammers through a lot of data. Yeah. So with this suggestion, the computation requirements are pretty stable because the time buckets now. It's much smaller, so less data is read. But yeah, at low frame rates, it then needs to read all the buckets because it then looks at the time margin. Yeah, so I don't know. I mean, I do like that aspect because low FPS runtimes need to do less. Okay, so that's my thought on this. The current implementation is fine, but it just, the size is outrageous. Yeah. Let me say the implementation approach is fine, but the data size requirements. So, and it would be possible to reduce size requirements by quantizing samples and moving intermediate samples into time buckets. Mm-hmm. Mm-hmm. Good. Then let me send my review. It took quite a while. Yeah. Mm-hmm. This test is redundant. Mm-hmm. Good. Then let me submit that. Mm-hmm. Okay, that was a really long review now. Mm-hmm. Okay, good. Then, yeah, I think that would be it then for this session. Only one review. Yeah. Mm-hmm. Okay. Good. Then that was 2 hours 30. We'll end it here. I wish you a great day or night. Until next time. Goodbye.